Welcome to this explainer. Today, we're cracking open an astronomical cold case where a single outcast star exposes some seriously violent secrets hidden deep in space. Our focus is an ancient globular cluster known as Caldwell 93 or NGC 6752. Now, globular clusters are these beautifully dense spherical collections of hundreds of thousands of really old stars, all tightly bound together by gravity. But right within this incredibly crowded stellar city, astronomers found something that just doesn't belong. An anomaly that ultimately revealed a dark, chaotic truth about the very heart of the cluster. Our main subject today is a millisecond pulsar with the catchy name PSR J1911-5958A. We're going to trace its journey to figure out exactly what happened to it. Let's kick things off with this absolute massive distance, 6.4 arc minutes, or over 3 half-mass radii. That is how far our subject is isolated from its home cluster's core. To put that into perspective, in a globular cluster, heavy objects naturally sink to the dense center over time through a process called mass segregation. Think of it like dropping heavy rocks into a pond. They sink straight to the bottom. So finding a heavy neutron star 6.4 arc minutes away, that's effectively the cosmic boondocks. It is the extreme outskirts, sitting roughly 57 core radii away from the center. Finding a millisecond pulsar just floating on the surface like this is incredibly rare, and it immediately had astronomers scratching their heads.
And just look at the sheer scale of this isolation. Over on the right, inside the circle, you've got the inner crowd, pulsars B, D, and E, all huddled up near the cluster's dense center. Then, way off to the left, all by itself, is PSR A. It's essentially sitting alone in the suburbs. Down at the bottom, you'll see another outcast, PSR C, which is also isolated but not quite as far out as our main subject. This visual starkly highlights the core mystery here. What kind of force is powerful enough to throw a heavy neutron star so far away from where it should naturally live?
Part 1. The Outcast of Caldwell 93. Let's look a bit closer at this anomaly. To really understand this puzzle, we have to look at the outcast itself. PSR-A isn't just far away. It's a rapidly spinning millisecond pulsar, rotating with a dizzying spin period of just 3.27 milliseconds. But here's the real kicker. It's not alone. It's actually trapped in an incredibly tight 20-hour orbit with a companion star. And this orbit is near perfectly circular, with an eccentricity of less than 10 to the negative fifth. This detail is massive. Why? Well, if you have a binary system and something physically kicks it hard enough to send it flying to the edge of the cluster, that kind of violent event almost always disrupts the orbit, making it highly elongated or eccentric. But PSR-A's orbit is practically a perfect circle. It's as if it was gently carried out there, which completely contradicts the extreme distance it traveled. Part 2. Identifying the optical companion. So, to figure out how it got stranded, astronomers actually turned to archival Hubble Space Telescope data to hunt for its cosmic accomplice. By analyzing the faint light coming from this exact spot in space, they struck gold. They discovered a faint blue object that turned out to be a low-mass helium-core white dwarf. Based on the data, it's sitting at roughly 0.2 to 0.24 solar masses. But the wildest clue was its temperature. Running between 11,000 and 16,000 Kelvin, this white dwarf is crazy hot compared to the rest of the cluster's stars. Now, a white dwarf is essentially the leftover core of a dead star, and they just cool down over time. The fact that it's still this hot, that tells us it hasn't been cooling for very long. In astronomical terms, it's actually quite young. Part 3, the age mismatch mystery. This is where the clues stop adding up. When you actually put the pulsar's data next to its companion, the whole story breaks down. We're looking at a staggering mismatch. You've got a 17-billion-year-old pulsar paired with a white dwarf companion that cooled less than 2 billion years ago. The pulsar's characteristic age is calculated based on how fast its spin is slowing down, which gives us that massive 17-billion-year figure. Meanwhile, the white dwarf cooling models confidently peg the companion's age at roughly 1.3 to 2 billion years max. Typically, in these recycled millisecond pulsar binary systems, the pulsar starts to spin down at the exact same time mass transfer stops and the white dwarf begins to cool. They should share the exact same age. But they don't. Which brings us to a huge question. How on earth can a tightly bound binary system have such vastly different ages? If they're locked together in this beautiful, tight 20-hour circular orbit, how can their historical timelines be so completely misaligned? How did a seemingly ancient pulsar end up partnered with a surprisingly young white dwarf, sitting completely isolated in the outskirts of Caldwell 93?
Part 4. A violent core ejection. Let's see how they got there.
The answer, it turns out, lies not in a peaceful birth, but in chaos. You see, the outskirts of a globular cluster are usually pretty quiet. The real action happens right in the dense core. And that young age of the white dwarf perfectly matches the time it takes to orbit out into the cluster's fringes, proving they were violently slingshotted out of the core recently. What likely went down is that, about 2 billion years ago, a star or an existing binary wandered a little too close to the cluster's chaotic center. An extreme gravitational interaction took place. This encounter likely stripped away material, creating the white dwarf we see today, while simultaneously acting as a massive gravitational slingshot, forcefully ejecting the newly minted binary out of the core and into a highly eccentric orbit around the entire cluster. That young age of the white dwarf is literally a timestamp of this violent ejection. This whole scenario points to something called non-thermal dynamics. Basically, this means the system was physically battered by something incredibly massive lurking in the center of the cluster. In normal thermal dynamics, stars just sort of gently exchange energy and settle into a nice, predictable distribution. But a millisecond pulsar getting chucked 6.4 arc minutes away, that requires a massive burst of energy. And remember, PSR C from earlier? The fact that Caldwell 93 has not one, but two ejected pulsars is a huge flashing warning sign that the core of this cluster is an incredibly hostile environment. And this data from the inner pulsars basically proves it. It reveals something shocking, a central mass-to-light ratio over 10, meaning the core is absolutely packed with heavy, invisible mass. I know this graph looks a little complex, but it's telling an amazing story. By timing the pulses of those inner core pulsars, B, D, and E, astronomers found they have huge negative period derivatives. In simple terms, they are accelerating rapidly along our line of sight, being violently pulled by the immense gravity of the cluster's core. But here's the catch. When you look at the light coming from the core, there aren't nearly enough visible stars to create that much gravity. To explain this acceleration, the core needs a mass-to-light ratio greater than 10, maybe even up to 13. That is vastly higher than any other globular cluster, which usually sit around a ratio of 1 to 3. This means the core is completely dominated by heavy things that do not shine.
Now, because the ejection didn't wreck PSR-A's perfectly circular orbit, the accomplice that kicked it out was likely a massive binary pair of black holes acting as a single point mass. Think about it. To kick a fragile binary system so hard that it flies to the absolute edge of the cluster without disrupting its perfect circular orbit, the scattering target had to be incredibly heavy and very compact. If it were just a loose group of normal stars, the complex gravitational tug-of-war would have ripped the pulsar binary apart or at least made its orbit wildly eccentric. But a pair of black holes would act like a single massive point, executing a clean, powerful ejection. This perfectly aligns with that crazy mass-to-light ratio data. Caldwell 93's core is teeming with dark remnants. It's a dense population of black holes.
Which leaves us with a pretty thrilling thought. If tracing the steps of just one single outcast can reveal a hidden nest of black holes, what other dark mysteries are waiting to be uncovered? PSR J1911-5958A is just one tiny, faint dot sitting in the outskirts of a single globular cluster. Yet, by simply observing its location, its tight orbit, and the age of its companion, astronomers were able to shine a light into the darkest, most crowded depths of Caldwell 93, revealing a turbulent engine of black holes. It really goes to show that in space, the biggest clues are often hidden in the most isolated outcasts. Thanks for joining me for this explainer, and remember, keep looking up.